Okay. These notes are on subspaces, and the definition of a subspace is really simple. Take some subset of a vector space, say U. If U is a subset of a vector space and it is a vector space in itself, then it is a subspace on V. And it also has to be a vector space in the same sense that V is a vector space. So it needs to have the same definition of addition and scalar multiplication, and it needs to be on the same scalar set, where be it real or complex, or real and complex. So if we know U is a subset of V, we actually know enough about U to start out with to not need all of our properties of vector spaces to check that it itself isn't a vector space. Because we know it's a subset of a vector space, we don't have to check as many properties. A lot can be ignored, and a lot of properties of vector spaces are implied by the fact that U is a subspace of V. And we only need to check three things. So we need to check that the identity vector is an element of our subspace. We need to check that it is closed under addition. So if we take two elements in our subspace, this must imply that the addition of those two elements or vectors are also in the subspace. And the last thing is that if we take some scalar in our scalar set and we multiply it by some vector in our subset of a vector space, then this is implied to be in our subspace as well. And these three things are all that you need to say that U, a subset of a vector space, is itself a vector space. And that also implies that it is a subspace on V, our initial vector space. And as a good example would be like, we're going to take all vectors in F2. So we're going to have our first element and our second element, where the first element is equal to 5 times the second element. And we're going to do plus 1. So it's all lists of length of 2, where the first element in the list is 5 times the second element plus 1. So let's check if this is a subspace on F2. So the first thing we should ask is our identity vector in this subset? So if we take 0, 0, is this in our subset? Because 0, 0 is the identity vector of F2. If this were a vector space, then it would also be the identity vector on this subset of F2. So it's pretty easy to show that this is not in our subset, because let's say the second element in our list equaled 0, which is a condition for the identity vector being in the first place. Then our first element would have to be 0 plus 1, which means we'd have this vector, if anything at all, and we could not have our identity vector. We have restricted the space we occupy in this subset such that there's no identity vector. So this is not a subset. This is a subset, but it is not a subspace on F2. All right, let's take the same thing, but instead we'll change the conditions that restrict some elements in the subset. So I'll take a list. We're going to say that x1 is always equal to 3 times x2. If let's take our identity vector and see if this is possible. So let's say our first element is always equal to 0, or let's say that let's take our first element and say it's equal to 0. Now we have we can derive our first element from the second element, and it is also equal to 0 because 3 times 0 is equal to 0, which means that this vector is in our subspace. Okay, and then the second condition is that it is closed under addition. So we need to show that for every vector in this subset, that an addition on those vectors will result in a vector that is a vector that is also in that subset. The result of an addition on any two arbitrary vectors in our subset is itself a vector in our subset. So let's take the first vector of y with its elements, and the second vector of x with its own elements. Because these are elements in U, our restricted subset, we know that x1 and y1 are equal to 3 times the second element in each of their lists, respectively. So we can just say, we can rewrite x1 as in terms of x2. So then we get this. And we can also rewrite y in terms of its second element completely, so that every element is in terms of its second element. Okay. And if we were to add them, we just get 3x2 plus 3y2, excuse me, and then x2 plus y2. This is our output vector, and then we can pull out our 3 and get x2 plus y2 as one factor, and 3 as the other factor in the first element in this vector. Okay, and then so basically we now see our second element in the composite vector as being as a constituent of our first term, in the same way that we've restricted elements in our subspace. So this x1 equals 3x2 is exactly the form that we see our resulting vector from this addition, because this is x2 and this is x2, and then it's multiplied by 3, and this is just this is shown to be an element of our subset in every sense. For any arbitrary vector that we add together in our subset, we will get another vector, some other vector in our subset. And then the third condition is that if we scale some vector, then we will get a vector in our subset. So take some arbitrary vector y, y1, y2. If we scale it by s, and we'll rewrite it, we'll write the first term in terms of the second term. So 3. If we scale by some s, it also should be in our subspace. So let's scale y times s. We get 3sy2 and sy2. Well, if this is our second element, we can see our second element times 3 in our first element in the list, and so this is contained in our subset. So these three conditions are met, which means that our subset is a subspace on our vector space of R2. And then, okay, so take all polynomial functions that exist. Okay. We know polynomials, or assume that polynomials are a vector space. And then take all polynomials where an input of 3 is equal to 0. Can we show that this is a subspace on the set of all polynomials? So is our identity vector or identity polynomial, is this in the set of polynomials where an input of 3 equals 0? Well, the identity polynomial is just the real value of 0. There is no input where 0 doesn't equal itself. So the first condition checks out. And then we'll say, are the polynomials where an input of 3 equals 0, are they closed under addition? So take some polynomial function g and add it to some polynomial function f. If you give them both inputs of 3, is this contained in the subset of polynomials that we're talking about? Well, we know that g of 3 equals 0 by definition, and we know that f of 3 equals 0 by definition. And so, two vector, if we take some composite polynomial made up of two other polynomials, it's also going to be equal to 0. There's no way around that. So it meets our second condition. And then the third condition is that it must be closed under scalar addition. So take some scalar in f and multiply it by a polynomial where an input of 3 equals 0. Well, f of 3 must equal 0 because that's what we've defined our polynomials to be. And so s times any scalar, or 0 times any scalar, is also equal to 0. And 0 is our identity polynomial. So the set of polynomials where an input of 3 gives an output of 0 is a subspace on the set of all polynomials. And that just shows you how abstract subspaces and vector spaces can get. As long as you've defined a scalar set to act on and scalar multiplication and addition, then you can say things about the real number plane, the real or complex number plane, and even functions themselves, all using the same system of linear algebra. So that's subspaces.